Achha, okay, now can everyone hear me? Hello.
Yes, we can hear you, sir.
Okay. So we did Lee Chatelier principle, which was kind of O levels. Uh, and we discussed yesterday. We discussed that if you increase temperature, the endothermic reaction is favored. You decreased temperature, the exothermic reaction is favored, and only for gases, if you increase pressure, less gas mole side is favored, and you decrease pressure, more gas is going to be formed. There's going to be more gas mole side that's going to be favored, and we also did that if you increase or decrease concentration, the equilibrium is going to do the opposite. It's going to favor that reaction that does the exact opposite. So if you decrease something, it's going to try and increase it. If you increase something, it's going to try and decrease it. So these were all the uh, the rules for equilibrium, which hopefully everyone knows. We'll do a worksheet, a small worksheet on this in a moment. And one thing that I wanted to, I don't know if I had discussed this. Uh, Maybe I had, maybe no, probably I did. I didn't. That thing is that when you talk about Lee Chatelier principle, and whenever you say that the forward reaction is going to be favored or the backward reaction is going to be favored, for example, in this reaction, you've got N2 plus 3H2, and it's in equilibrium with 2NH3, right? So there's your Haber process reaction. The enthalpy change for the forward reaction, enthalpy change is always given for the forward reaction, it's minus 88 kilojoules per mole, which is negative. That means that indicates that the forward reaction is the one that's uh, exothermic, and your backward reaction is the one that's endothermic. The backward reaction is always going to be the exact opposite. So you have this reaction. So whenever you talk about equilibrium, never ever confuse or mix up equilibrium with rate. Equilibrium with rate of reaction. They're two completely separate things. When we talk about equilibrium and when we talk about Lee Chatelier principle, when we say that one of the reactions is favored, it's always a relative comparison. Which means you're comparing the two reactions. I mean, for example, if I state that if I increase temperature, which of the two reactions is going to be favored if I increase temperature?
The backward.
The endothermic reaction, right, which is the backward reaction. So if you increase temperature, that's the rule. That's the Lee Chatelier principle. Whenever you increase temperature, at a higher temperature, endothermic reaction, which is the backward reaction, that's going to be favored. Endothermic or backward reaction is the one is favored. Now, what that statement actually means is that's a relative comparison. It doesn't mean it's not talking about the speed of the reaction. It just means that the backward reaction, what it means is that the backward reaction in comparison is faster compared to the forward one. So it's faster compared, so it's a comparison, it's compared to the forward one. Maybe both of them are decreasing in speed, maybe both of them are increasing in speed. So backward is faster compared to the forward reaction. So it's a relative comparison. It just so it's not an absolute comparison. It just means that the backward reaction would be faster compared to the forward one. Maybe both of them are decreasing in speed. Maybe both of them are increasing in speed. But still, the backward is faster compared to the forward one. Is this idea clear?
Yes.
Okay. So remember, it's always a relative comparison, and and the questions usually mix the two things up. I mean, that's what they're trying to actually get you confused with. They always mix this up. And when they talk about rate, always remember that if you do the following things, the rate of the reaction, whether it's the backward or the forward, we don't really care. So be very careful. Is the question talking about equilibrium? Remember, equilibrium is a relative comparison. If it's talking about the Le-Chatelier principle, that thing is a relative comparison. But when it talks about rate, then you just have to talk about the rate of the reaction. You just have to talk about whether the reaction is speeding up or decreasing. So when does the reaction increase in speed? If you've got a higher temperature, then always remember you get a faster reaction. Higher temperature, or you have higher concentration or higher pressure. So if you have higher concentration or if you have higher pressure as well. At higher pressure, particles are closer together, so they would bump into each other more, so you're going to get more frequent collisions. At higher concentration as well, the particles are closer together. They're more particles, so they're closer together, so they're going to bump into each other more. Higher temperature, also the particles have more kinetic energy, so they travel faster, and they're going to bump into each other more. So there's going to be more frequent collisions, plus the collisions are going to be more effective as well, more successful, more violent as well, because if they have more kinetic energy. So in all three cases, and there are two more factors that affect the rate of reaction, but since those two factors have nothing to do with equilibrium, so I'll just, one is surface area. So I'll just write that in brackets. So you can have higher surface area, or you can add catalyst as well. These would also speed up the reaction. So whenever you have these conditions, or the opposite of these conditions, it's always going to be a faster reaction. So you don't really care it's the forward or the backward reaction. So when the question is talking about the rate of reaction, then then it's not a relative comparison. It's just talking about whether the reaction is speeding up or slowing down. So if you're doing this at a higher temperature, the reaction is going to be faster. Whether it's the backward or the forward reaction, both of them are going to be faster. So for example, over here, right now we were talking about equilibrium, right? I said that higher temperature, and we stated that the endothermic or backward reaction is favored. Now, immediately they might ask a question about the rate of reaction. They might ask, if you have a higher temperature, what happens to the rate of the forward reaction? Remember, if this equilibrium is attained at a higher temperature, both the forward and the backward reaction both are going to speed up, because at higher temperature particles have more kinetic energy. So not only the forward reaction but also the backward reaction, any reaction, whatever it is, it's going to speed up at higher temperature, or higher if the particles have higher concentration, or if the pressure is higher, both the forward and the backward reaction, both of them are going to speed up. But what equilibrium states is one of them is still going to be faster compared to the other one. So do you get the difference? Is this clear?
Yes.
Yes.
So you have to be very careful, because in the same question they're going to ask you about equilibrium, and somewhere in the middle they would start talking about rate of reaction. So remember, don't confuse with this, that people think that the backward, like you wrote that the backward reaction is faster. So it's not a comment on the speed of the reaction. It's just a comparison. Like one of them is faster compared to the other one. Maybe both of them are slowing down. Maybe both of them are speeding up. The speed of the reaction is determined by all these conditions. So I'm going to do just a simple question over here, and let's do a simple question. We've got SO2 plus O2, and it's forming 2SO3, and they're all gases. So they're asking state where would the equilibrium position shift if you, what would be the equilibrium position, forward or backwards, if you do the reaction at high pressure?
Forward.
Okay, so higher pressure, you're basically compressing it, you're squeezing it, so there's less room for gas to be formed. This side has more gas, this side has less gas, so it's going to move forwards, less gas mole side. So so the answer for that would be less gas moles side is going to be favored. Which is the forward reaction. So it's going to be the forward reaction. So that's question number one. And right with question number one, they might ask you about a second question, which would be what's going to happen to the speed of the backward reaction at higher pressure. So what's the answer to that? You've increased pressure. So at higher pressure, what would happen to the speed of the backward reaction? Can you even answer?
It will slow down.
What did I say about, I mean, this question is about the rate of reaction. What did I tell you about rate? That whenever you have higher pressure or higher concentration or higher temperature, what happens to the reaction? It's going to be faster. Is that clear?
Yes.
TK, you're going to get a faster reaction. But again, the forward is going to be favored. That means the forward would still be faster compared to the backward. Both of them would speed up. At higher pressure, whenever you take the reaction at higher pressure, the reaction is going to speed up, whether it's the forward or the backward, because the particles you're compressing it, the particles would be closer together, so they're going to bump into each other a lot more. So forward reaction would speed up, and the backward would also speed up. Both of them would speed up. So when they're talking about the speed of the reaction, then they're not talking about the relative comparison. Uh, so both of them are going to speed up at higher pressure, whether it's the backward or the forward. Any reaction would speed up. But what this first statement states is that the forward would still be faster compared to the backward one. So both of them are speeding up, but the forward would still be faster compared to the backward one. Is this clear to everyone?
Yes.
Yes.
Okay, so I'm just insisting this again. Just don't mix equilibrium with rate. Be very careful. Is the question talking about rate or is it talking about equilibrium? So always keep this in mind. You have to read the question very carefully. So we're going to do a worksheet on Lee-Chatelier principle. Just one second. So maybe it's worksheet on Lee-Chatelier principle. Now starting with the first question. So the first question is about there's a swimming pool and water can be kept free of harmful bacteria by adding sodium chlorate, NaOCl. So it probably contains OCl minus 1 ions. So those are coming from here. Remember, group 1 salts are very soluble, so they dissociate. They always dissociate. NaOCl in water, the Na ions and OCl minus 1 ions, they would be separate. So this reacts with water to produce HOCl molecules, which are seen over here. So this over here is a reversible reaction. So the Lee-Chatelier principle would, I mean, the reaction could shift forward. It could also shift backwards. And then he's saying that in bright sunlight, the OCl minus 1 ions that you added in water, they would be broken down by ultraviolet light, and you get this reaction. Now, this reaction is not a reversible reaction, so that means the reaction can go forward, but it can't move backward. So it's not Lee-Chatelier principle doesn't really apply to it because it's not going to move backward. So which method would maintain the highest concentration of HOCl? Now you can't really do much about this reaction because it's not going to move backward. He's saying how can you maintain a higher concentration of HOCl? So what we are looking for is we want the equilibrium, the first equilibrium to shift to the right? So starting with let's start with D. Bubble air through water. Now, what does air contain? It contains O2, right? And where do you have O2? O2 is over here in the second reaction. The second reaction is not reversible. So if you add more O2, if you take out O2, nothing would happen. So adding more O2 or air, I mean, the first reaction has no air in it. The second reaction has oxygen, which is probably coming from air, but nothing would happen to the second reaction. So the second reaction has nothing to do with HOCl. So it can't be D. Is that clear?
Yes.
Yes.
So now, if you add a solution of hydroxide ions, if I add more OH ions, where would the equilibrium shift? I'm talking about C. If you add more hydroxide ions, where would the equilibrium shift? Backwards or forwards?
Backwards.
Okay, so if you add more OH ions, the equilibrium is going to remove OH ions. So it's going to shift backwards. We don't want it to shift backwards. So we want it to shift forwards. We want to increase the HOCl concentration. We want to make more of it. As a similarly, add a solution of chloride ions. Now chloride ions have nothing to do with this equilibrium. They're in the second one, and that's not reversible. So you can't really do much about it. So even if you add more Cl ions, nothing would happen to it. So that's out of the question. So the answer is the first one. Acidify the pool water. So that means you're adding acid. Acid contains H plus 1 ions. So you're basically adding H plus 1. Now, can anyone explain to me why would adding H plus 1 ions shift this equilibrium to the right? Any idea? Like this one has no H plus 1 ions. So why would adding an acid to the pool water or adding H plus 1 to the pool water would shift this equilibrium to the right? Anyone, any idea? Just make a random guess.
Maybe because if you add more H plus, then you're gonna get more water.
Would it react with water? What would H plus 1 react with? Let's talk about that. H plus 1 reacts with OH ions. I mean, this is an acid-based reaction. Like you acidify the pool, so acids have H plus 1, bases have OH ions. So H plus 1 would react with OH ions to form water, right? So what's going to happen to the quantity of OH ions? The quantity of OH ions is going to decrease because they're going to get neutralized by H plus 1. Is this clear?
Yes.
So that means the quantity of OH ions it's going to decrease. And if it decreases, the equilibrium would try to make more of it. So it's going to shift to the right. And if it shifts to the right, more HOCl would be formed. Hence, its option A is the correct one. Is this clear?
Yes.
So remember that they're going to ask you questions where they're going to add something that would react with something that's in the equilibrium, and its quantity would decrease. Like in this case, it's H plus 1 that's being added, and when H plus 1 is added, the OH ions would react with it, and the OH ion quantity would decrease. And because of that, the equilibrium would try to make more of it, and it would shift to the right. So that's this one. Let's move to the next one. Increasing the pressure increases the equilibrium yield of SO3. Where would the equilibrium shift in this case? If I increase pressure? Like less gas or more gas? Anyone? Alicia?
More
If you increase pressure, remember if you increase pressure, where did the pressure thing go? This one. If you increase pressure, you're basically compressing it. There's going to be less gas that's going to be formed. If you increase pressure, less gas mole side is favored. So you're basically compressing it. So there's not enough room for gas to form. So there's always going to be less gas formed. Vice versa, if you decrease pressure, you're basically pulling the piston up. You're increasing the volume, and more gas is going to be formed. So in this case, which side has less gas? It's the forward side. It just has 2 moles of gas, whereas the backward side has 3 moles of gas. So less gas. So the yield is going to increase. That is true. It increases the yield. Is that clear?
Yes.
So we're not going to discuss KP yet. What does a catalyst do? Actually, we didn't study catalyst. We did mention catalyst somewhere at the end. I'll just mention catalyst. What does a catalyst do to the equilibrium position? Does it favor the forward, backward, which reaction? Anyone?
Forward?
I said, what does a catalyst do? I said, remember, a catalyst, like by definition, a catalyst speeds up the reaction. But it speeds up both forward and backward reactions. Equally. So that means the equilibrium position does not change. For example, if I have H2 and I2, and it's forming 2HI, right? So every second, let's say 10 molecules of HI per second are formed. And the rate of the backward reaction is also the same. So every second, 10 molecules of HI decompose into H2 and I2 back again. So the quantity of HI remains constant. And the quantity of H2 and I2 also remains constant. Like forward and backward rate are equal. Now, when you add a catalyst, all of a sudden, the rate of forward reaction would increase, but the rate of backward reaction would also increase. So instead of 10 per second, 20 molecules of HI would be formed. But at the same time, the backward would speed up as well. So 20 molecules of HI are going to be decomposing back again. So the quantity of HI would remain unchanged. Nothing would happen. The equilibrium position stays exactly where it is, except for the fact that it's now a faster reaction. So both forward and backward reactions speed up. No change in equilibrium position. I mean, it's not going to favor the forward or the backward. It's going to favor both of them. So no change in equilibrium position. Is this clear?
Yes.
Yeah.
So the equilibrium position kind of stays exactly where it was previously. So now so the presence of a catalyst increases the, it doesn't, it stays exactly, I mean, you get a faster reaction, but the amount of SO3 remains exactly the same. It's not going to increase or decrease because both forward and backward reactions would speed up equally. So 3 is not an option. Next one is, which statement about reversible reactions are correct? The first one is increase in concentration of a reactant always increases the concentration of the product. So that's the first statement. Reactants, equilibrium. He's talking about a reversible reaction. Products. So if I increase the concentration of the reactants, where would the equilibrium shift?
Forward.
Okay, so if I increase concentration of the reactant, it's going to try and decrease it. So it's going to convert that into products. So increase in concentration of a reactant, it's definitely going to increase the concentration of the product because forward reaction is going to be favored. Okay, is that clear?
Yes.
And then number 2, an increase in temperature always increases the rate at which the equilibrium is established. Now remember, this one is not a statement about equilibrium. He's talking about you increase temperature, will the rate increase? And will it always increase? Whenever you have a higher temperature, what happens? You have a faster reaction. So whenever you increase temperature, you always increase the speed of the reaction. That's always, it's always going to happen uh, because you're going to have more. At higher temperatures, the reaction is always faster, whether it's the backward or the forward. So is that clear? This statement is also true. DK, is this clear?
Yes.
And the last one is that an increase in temperature always increases the concentration of the product. So now this one is about equilibrium because he's talking about increasing the product or decreasing the product. So when you increase temperature, which reaction is favored? Forward or backward?
Backward.
Like, how do you know it's going to be backward? If you increase temperature, what's the rule? Whenever you increase temperature, where did it go? Just a second. whenever you increase temperature, which reaction is favored? The endothermic reaction is favored. So we don't know which one is the endothermic. Like, it could be the forward reaction that's endothermic, or it could be the backward reaction which is endothermic. We don't know, because we don't, like, reactions can be endothermic, they can also be exothermic. So since we don't know is the forward endo or exo, we can't really tell. So this always thing wouldn't really work. It would only work that if you increase temperature and the forward reaction is endothermic, then that's the one that's going to be favored, and the backward is exo. But we're not sure. Maybe the forward is exo and the backward is endo. Is that clear? So 3 is wrong because it's not going to be always. Is that clear?
Yes.
Yes.
So then you have next one. He's again saying, what would alter the composition of the equilibrium mixture in favor of V2 plus ions? So you want the equilibrium to shift backwards. I mean, you want V2 plus ions to be favored. You want more of V2 plus ions. So if you add an acid, like if you add H plus 1 ions, there is no H plus 1 ions in the equilibrium, but what would H plus 1 react with?
OH minus.
Okay, they're going to react with OH minus 1. So the quantity of OH ions would decrease. And if it decreases, where would the equilibrium shift? Forward or backward?
Forward. Forward.
Forward. It's going to try and make more OH ions. It's going to do the opposite. So we don't want it to move forward. We wanted it to move in the backward direction. So the first one is definitely wrong. Adding a reagent that selectively precipitates V3 plus ions. What does that mean? This is about precipitation. So I'll just quickly explain what precipitation is. You've studied this in O levels as well. So what is precipitation? You remember that all salts have different solubilities. Like if you have a beaker and the beaker has a bunch of, it has a solution and it has a bunch of ions. Like it has NaCl. So that means there's going to be Na ions and there's going to be Cl ions, more Cl ions, more Na ions. NaCl would be completely dissociated and the ions would all be randomly just floating around in water. That is what happens when you stir it with a spoon, normal table salt added to water, and you stir it. So all the ions are separate. They are surrounded by water molecules and they're all randomly just moving around. So what is precipitation? Precipitation is NaCl dissolves, which means that the ions get scattered in water. So what is precipitation? Precipitation is the reaction in which that you add a substance like I'm going to add silver nitrate. Now that's also soluble. So if I mix silver nitrate, the silver ions and the nitrate ions and the silver ions, they all get dissociated as well. And these ions are also randomly just moving about. And I mean, the silver nitrate is also soluble. So now what's going to happen is that when you mix two soluble substances, especially ionic compounds, uh, the two substances, their ions would randomly start mixing with each other. And in that process, this might happen that the Ag ions and the Cl ions might combine together. So the Ag plus 1 ions from silver nitrate and the Cl ions from NaCl, they might combine to form AgCl, and this AgCl is insoluble. If you remember, chlorides are all soluble except for silver and lead and mercury. So apart from 2, 3, all of them are soluble. So what would happen is that your silver ions and your chloride ions, they would start forming a precipitate. So you would start seeing a solid of AgCl solid being formed. And this would continue to happen. I mean, these two would combine, right? And they would do exactly the same. The Ag and the Cl ions, they would combine together to form another AgCl solid. So this is what precipitation is. Is that clear?
Yes.
But for that, you have to remember which compounds are soluble, which compounds are insoluble. Now he's saying that you're adding, in this question, he's saying that you're adding a reagent that selectively precipitates V3 positive ions. So basically, the ions, I mean, you might add some other substance, like you can add NaOH. That could be your reagent. The NaOH is soluble, so it's going to contain OH ions. OH ions would be floating in water. The two might combine together to form a solid, which is VOH3, which is kind of insoluble. I'm assuming it's insoluble. We don't know what the solubility of vanadium is. But the point is, the solution is going to have fewer V3 plus ions because they're all going to form a precipitate. So the quantity of V3 plus ions would become lesser because they're all forming a precipitate. So where would the equilibrium shift?
Right side.
Okay, so that's again wrong. It's because all the V3 plus ions would be gone, they would form a precipitate. So the equilibrium would try to make more V3 plus ions. It's going to try and do the opposite, and it's going to shift to the right. Allowing the hydrogen to escape as it forms. If you remove H2, where would the equilibrium shift? It would do the opposite. It's going to try and make more H2, so it's going to go in the forward direction. As the last one is correct, it's making the solution more alkaline. That means you add more OH ions. If you add more OH ions, it's going to try and decrease the OH ions, and it's going to shift in the backward direction. ठीक है, is that clear?
Yes.
So now next one is you have an industrial process, and he's saying two gases X and Y react together to form a single gaseous product Z. The percentage yield of product Z varies. So they've given you a graph now. Now they haven't told you which one is endothermic or which one is exothermic. We don't know is the forward endo or exo. But first thing, can you guess from the graph, is the forward endo or is the backward endo? Like what's happening? On this axis, I mean this axis over here, you have the amount of Z. So what's happening to the amount of Z? This is a lower temperature, and this graph is for one that has a higher temperature. So what happens to the amount of Z? If you have a lower temperature, if you decrease temperature, right? If you decrease temperature, if you lower the temperature, the amount of Z or percentage of Z at equilibrium is 90% or around 90%. That means there's more forward reaction happening. And there's more Z being formed. Like you're getting 90% at a lower temperature, you're getting more percentage of Z. At a higher temperature, you're getting actually lesser Z. So is this statement clear?
Yes.
And what does the equilibrium state? When you decrease temperature, which reaction is favored, exo or endo?
Exo.
So that means the forward reaction is, because the forward reaction is being favored, by looking at the graph, you can figure out that the forward reaction is, you're getting more and more Z as the temperature is lowered. So that means if you decrease temperature, the exo reaction is favored. That means the forward reaction is the exo reaction. So that indicates that the forward is exo. And vice versa, the backward is the one that's going to be endo. Because at a higher temperature, endothermic reactions are favored. So the reaction would start going in the backward direction and less Z would be formed. So at a higher temperature, you're getting lesser Z. So this is something that we have figured out. So which statement about this equilibrium reaction is correct? Is correct. The reaction is exothermic in the forward direction. That's the statement that's correct, which we figured out. Okay, is this clear? France, is this clear? Anna, clear?
Yes.
Now, this one. So remember, enthalpy change is always given for the forward reaction. That means the forward is it's positive, so that means forward is endo, and the backward is the one that's exo. Now the question is, if the temperature of an equilibrium mixture of gases is increased at constant pressure, will the volume of the mixture increase or decrease in Y? So read the statement. If the temperature is increased, so you increase temperature, which reaction would be favored, exo or endo?
Endo.
Okay, so endo is going to be favored. So it's going to go forward, right? So it's going to move to the forward reaction. So will the volume of the mixture increase? Will you get more gas if the forward reaction happens?
Yes.
You're going to get more gas because if the forward reaction happens, which is endo, I mean, we figured this out. If forward reaction happens, one molecule changes into two molecules of gas. So you're going to get more gas. Is that clear?
Yes.
Achha, so you
Yeah.
get more gas, right? So the volume of the mixture will increase, right? It's the first two statements. One of them is correct. So why is it increasing? Because the equilibrium is shifting to the right. So because the shift of the equilibrium towards the right. So that statement is correct. And that statement is also given in the second statement as well, because the shift of the equilibrium towards the right. So up till this point, both statements are kind of identical. This one is also saying that it shifts to the right. The second one is also saying that it shifts to the right. But he's saying, and also because of thermal expansion. So is that statement the third? So the second statement, B, option B, has a third point as well, that the volume of the mixture is increasing because there's thermal expansion happening. So when you increase temperature, what happens to the volume of gas? And you forget equilibrium. What happens if you have a gas and you've increased temperature? What's going to happen? Is it going to expand or is it going to contract? If you increase temperature, anyway, what's going to happen?
It's gonna expand.
It's going to expand. Like if you have a balloon and it's a hot day, the balloon explodes. Why does it explode? Because it starts expanding. The gas starts expanding, and the rubber eventually ruptures. On a cold day, the gases shrink. So there is going to be thermal expansion, no matter what happens to the equilibrium. So there are two reasons why the volume is, even if it wasn't an equilibrium reaction, the volume would still increase because of thermal expansion. Whenever you have higher temperature, the gases expand. So in this case, there are two reasons. One is that the equilibrium is shifting, so you're obviously getting more gas, or the quantity of gas doubles. One molecule changes into two. And the second one is also thermal expansion. That's also correct. Next is you've got these two containers and there's this mercury over here. So it's saying when the temperature is increased, which gas in bulb R would cause the mercury level in the right-hand limb of the manometer to rise? So first thing, there's a thermostat and he is trying to increase temperature, right? So you're trying to increase temperature. And he's saying that the manometer mercury on the right-hand side should rise, right? Would cause the mercury level in the right-hand limb of the manometer to rise. So that means there's only one possibility, that in the left-hand limb, more gas is being produced. So if you get more gas, the gas pushes the mercury and the mercury rises on the right side. Is this idea clear?
Yes.
So you're looking for, I mean, he's now asking what is X. So you have to have the amount of gas must expand. There should be more gas. So the first one is there's this reaction and the delta H is positive. So if you increase temperature, equilibrium would shift in what direction, forward or backward? I mean, delta H is positive. That means the
Well,
forward. It's going to shift to the right, right? Because it's endothermic. The forward reaction is endothermic. So that means you're going to get more gas. One molecule changes into two molecule. So the first statement is correct. You're going to get more gas, and the quantity of gas doubles. One molecule changes into two molecules. So the gases would push, and the mercury on this side would rise. So the first statement is correct. Second statement is you've got this equilibrium mixture. Now, would you get more gas? Like, does it really matter whichever position the equilibrium shifts? Like, if it goes forward, you still get one molecule of gas. If it goes backward, you still get one molecule of gas. So over here, it doesn't really matter where the equilibrium shifts. You're never going to get more gas. Is this clear? Because both sides have the same gas volume. Is this clear?
Yes.
Yes.
So in this particular case, it doesn't really matter. You're never going to get more gas. So that is wrong.
But what about thermal expansion?
Nee, but the thermal expansion is happening here as well, and the thermal expansion is happening because you're increasing the temperature of the entire thing, right? So the thermal, because of thermal expansion, that would get cancelled out. Like this gas is expanding, right? At the same time, this gas is also expanding. So the thermal expansion part kind of gets cancelled out. Is that clear?
Yes.
So which is why thermal expansion is not going to be a factor in this case. Because that other side would also thermally expand. And the last one is nitrogen. If you have got nitrogen on both sides, nothing would happen. Like even if that expands, this expands, they both would cancel out and the mercury stays right in the middle. So the last one, if you have nitrogen over here, you've got nitrogen on the other side as well. So it doesn't really matter. The same pressure would be applied on both sides. And the mercury stays exactly where it was. ठीक है, is this clear?
Yes.
So let's continue. I'll send this worksheet. Let's continue tomorrow now, and we'll start with we'll do some more questions, but we'll start with KC and KP. So, okay then. Take care, everyone. Allah Hafiz.
Bye, sir.
Yes.